All right, we're going to do our first full E&M practice exam today. So again, we're just going to follow the AP timing. I do write for the test, so I have a really good idea of the sorts of things we actually ask. So I tried to structure this as real as possible. So I tried to model difficulty. I tried to model time constraints, although of my two forms, this is definitely the easier of the two. I'll get around to making my second one later. So we'll just start with our multiple choice today. So we're going to do 40 questions. It says average of 2 minutes per question. I probably won't reach that because I talk a lot and I'm going to go in great detail about all the things. If you haven't done this beforehand, I'll make sure to link the test. It's much more worthwhile if you do it first before looking through solutions. We're just going to do the MCQ today. So target length will be about 80 minutes. We'll see if I reach under that because I have to do a lot of talking. All right. We'll give some meta tips kind of as we go on here. Like the first one being, we try to give you some confidence by making the first question an easier one. Similar to the end, we try to get you a win at the end as well. But we start off with some easy ones here. 3 charged spheres are placed along the x-axis, and we want to compare the net force on each of them due to the others. So if we just start, this is just Coulomb's law. So we see that my left blue sphere would exert a large repulsive force on 2 and a small repulsive force on 3 due to distance. My middle sphere would exert a large repulsive force on the other 2 spheres. And then my rightward sphere, number 3, would exert a large repulsive force on 2 and a small repulsive force on 1 due to distance. So notice that we see some cancellation happens right here in the middle. And by symmetry, these forces are equal and opposite for 1 and 3. So that would be C. So actually, we could have just selected that if you saw that the forces had to cancel on 2. So I rank that an easy one. Circuits shown below are identical with their bulbs and batteries. They're just wired different. So we have to figure out which circuit has brighter bulbs with justification. So it looks like we can talk about either resistance or potential difference. And potential difference should make sense because we said brightness is related to power. And we have 3 expressions for power. One of them is the definition, the other 2 we acquire from Ohm's law. But notice that since the bulbs have the same resistance, this quantity is the same, R, so we can actually just compare the potential difference. And that's actually a really easy task to do if we look at our color coding model for potential. So remember that for potential, we say that the top of the battery would be at high potential. The color explores all possible paths until it hits barriers. And then our low potential end of the battery, that's going to be our blue color. So notice we actually get the full potential drop across each bulb in circuit 1. So it is going to be circuit 1 that has the brighter bulb. For that reason, it has the full battery voltage, red to blue. But if I try circuit 2, the series one, same idea, except I ran out of colors. So I actually need a third intermediate potential. And this should make sense that it's going to be brighter in parallel because you get the whole battery voltage dropped across there in circuit 1 in parallel. And if you've ever played with circuit kits, you know that the brightness is larger in the parallel configuration. And this is why, right? Because you have a Kirchhoff loop where you have to drop part of the battery across each in series, but you get the full battery. There. All right, 2 Gaussian surfaces, which are spheres, are drawn near a bar magnet. Surface 1 encloses the north pole of the magnet, and surface 2 does not enclose any part of the bar magnet. We want to compare the flux through each of the 2 surfaces. So if you know Gauss's law for magnetism, you actually can get this instantly because we know that we actually have what are called closed surfaces. Closed means like a 3D shape. There's an in and an out. It's not a flat loop, it's a 3D shape. So Gauss's law for magnetism actually says that through any closed surface, the net magnetic flux is 0. So we should be able to instantly select this one, that the net flux is 0 through both surfaces. Now, why is that the case conceptually? Well, Gauss's law for magnetism really says magnetic field lines form closed loops. You can't have monopoles. So if I try to draw myself a very large field line here, maybe something like that. I mean, that's kind of an awful field line, but you get the idea. So it will definitely be clear that this field line enters surface 2 and also exits surface 2. So it's clear that flux is 0. But also, we have the property of magnetic field lines that say they form closed loops. So the fact that a magnetic field line always closes in on itself means you cannot have a net flux through a 3D surface because there's a well-defined in and out. Comes in here, exits here. So that's that. I would actually rank that a level 2 problem. Oh, I guess my circuit one. I rank it level 1 because series in parallel. Yeah, I'd rank this a level 2 because most people will understand that this flux is 0, but remembering the closed loop property reverses the north-south rule. Makes that a bit tricky. All right, calculate the power input from the battery in the circuit shown below. So we just want the power of the battery. And we have 3 lovely power formulas to choose from. How do you know which one to use? Well, it's the one that doesn't involve the missing thing. So notice we have a voltage for the battery, and we also have a bunch of resistances. So we're missing current. So if we look at our list of our 3 powers that we can get, of course you could. There's not like a wrong choice. There's just a most efficient choice. Notice we want the not centripetal acceleration one, v squared over r. And for the battery, that's just sort of smushing the circuit down into one object. So I can say that the total power is just going to be delta V for the battery squared divided by the equivalent resistance of the circuit. So we're really just looking to find REQ because we know the EMF is 10 volts. So what's REQ? Well, that's not terribly difficult because REQ, I have a 3 ohm in series with this 4, 6, 12 parallel combination. So we use the reciprocal rule for the parallel. And you can type this into your calculator. You'll see that 6 and 12 make 4, and 4 and 4 make 2 in parallel. So this would be 3 plus 2, which is 5 ohms. How nice. That's going to divide our battery EMF. So our battery EMF was 10, so we squared 10 volts, and then REQ was 5 ohms, and that will be 20 watts. 100 divided by 5 is 20. So this is very borderline. I barely called this easy because you're really just finding REQ. Now you could make the argument that there's 2 steps here, so this should actually be level 2, but it's borderline. All right, now we got some charges and a triangle, and we want the field at the missing vertex. So as per usual, we use superposition, which means draw both fields. So positives are sources of field lines, and negatives are sinks for field lines. So what's going to happen here? Well, notice that they're both pulling or pushing to the right, but they're competing up and down. So those 2 effects will exactly cancel each other, leaving a net field to the right. So what's the net field here? Well, the net electric field can be found by taking the field from both charges, but we don't want all the field from each charge because the up and down vertical part is going to cancel. So we only want the horizontal field. And if we're using our polar angle, we can extract that just by using cosine. Because we have 60 degrees everywhere because it's a nice equilateral triangle. So this angle up here is 60, polar angle. And then what is E from a point charge? Well, E from a point charge is just KQ over R squared with our distance L. And cosine of 60 is 1/2. Take that into your calculator if you don't trust your unit circle skills. And coincidentally, this actually works out to the field strength of just a singular point charge. Because we have 2 fields, but each of them is contributing 1/2. And you can see all the trigonometry mistakes that happen or lack of doublings that give you all the distractors. This is level 2. Borderline 3, but It's really just picking the right trig function and doubling it. All right, resistivity. So we have two wires that have length L. They have different areas, and their resistivities are determined by this function. So we do have like the base formula that says resistance is equal to rho L over A for constant resistivity. But if you don't have constant resistivity, you have to integrate the resistivity times the wire chunk divided by A. So we'll just do that twice and figure out the ratio. And this is not the easiest because we're changing A and we're changing the resistivity function. So it might be hard to totally reason what that should be. So let's do X first. So X is going to be, well, X has an area of just A. So we'd get the integral of rho 0 times X over L dx divided by A, going from 0 to L. So we would get rho over LA times X squared over 2, evaluated from 0 to L. One of the L's will get canceled from the denominator. So that's going to be 1/2 rho not L over A. So we get an effective resistance of 1/2. Now for Y, it's going to look very similar, except now we're just squaring the X and L that live up here. And our area is now 2A. So we'd get rho 0 over 2L squared A times X cubed over 3 from 0 to L. So now if we plug that in, L cubed, that cancels two of the L's down there, and we get a 3 on the bottom, so we get 1/6 rho not L over A. So notice that our X has an effective resistance of 1/2, our Y has an effective resistance of 1/6. So how do I get from 1/2 to 1/6? Well, this would be times 1/3. So should be clear by the number of steps happening here. This is clearly a 3-star. This is advanced. Pretty hard. So I'd rank that hard. All right, a Gaussian cube of side length 0.2 meters is drawn in a region of electric field, and the field is different at each of the surfaces. We want the net charge enclosed. So when we see field and talk about enclosed charge, we should be thinking Gauss, because Gauss says that the flux can be found by, this is going to be constant, so we can write it as EA is one way to find flux, or we could say that's also equal to Q enclosed over epsilon naught. Okay, and also we can just do some eliminating first, because notice what we have here is we have some field lines go in, but more field lines go out. So that must mean that we're hiding some sort of charge inside the cube. And if it's spawning field lines, it must be a positive charge. So we must have it being one of the positive options. So we actually know it's going to be positive. So what is the flux? Well, our net flux would be the flux out minus the flux in. So our outward flux would be EA, that's out. So this would be 15,000 newtons per coulomb times the area. So what's the area here? Well, it's a square of side length 0.2 meters, would be that shaded area. And then we get rid of 5,000 times 0.2 squared would be our into flux. And let's see, can I do that in my head? 0.2, that's 1/5. We can write this as, the difference would be 10,000 times 0.2 squared. And I believe that would be 400 would be our flux. But then we're not done, because we can set our 400 equal to Q enclosed divided by epsilon naught. So Q enclosed would be equal to 400 times 8.85 times 10 to the negative 12th is epsilon naught. And if we work that out, notice you can tell what answer it's going to be because we have 400, and then we have an 8, so that's going to make like roughly 3. So we get the 3.54 times 10 to the negative 9th answer. So yeah, it's computationally intensive, but it's still a level 2, I'd say, because you're subtracting the flux. You can actually work it out if you were to guess what my distractors would be. You could do this with only mental computation. So you get the sign correct by knowing it's a source. And then you get the number correct because you can imagine this is what you get if you add the flux contributions instead of subtract. So level 2 for that reason. And also, test taking tip, if you see numbers, do not do that question until the end unless you absolutely know what to do, because this is a lot of typing. All right, two spheres of charge plus Q are situated on the x-axis. One of them is frozen in space. The other one is let go. We want the speed of the other one after a long time. All right, well, if we want speed in this class, it is probably energy if you have a two-stage system. So this is going to be energy. Now, what version of energy do we want? Probably just a kinetic and potential conservation one. We probably don't need electric potential going on here, right? Because at the beginning, we're going to have electric potential energy and no kinetic. And then at the end, we're going to have no electric potential energy, and we're going to have all kinetic. So this is really just a K plus U equals K plus U problem, because if we release our sphere and let it go far, far, far away, the potential energy of the system goes to 0, and it can't just vanish, so it got turned into kinetic. So we can set up something like this. Electric potential energy would be KQQ over R. So no square. And if you're far, far away, you have no potential energy between the two, because it would cost 0 energy to bring those two very far apart from one another. So this just becomes 1/2 mv squared equals kq squared over d. Multiply by 2, divide by m, take a square root. Vf would be square root of 2kq squared divided by md. Doctor. Okay, so what would that be? That looks to be d. So I would rank this level 2. It is energy conservation, but also you can eliminate these because they have squareds in the denominator, and you can guess that the 1/2 comes from kinetic. So this would rank kind of nicely in level 2. Small charged sphere is moving at a known speed between these two charged plates. We know the magnitude of the electric field, and it's given that if this is at constant velocity, what is the B field? So this just becomes force balancing. So if I draw my forces here, we actually know from the sources and sinks rule that E must be up. And a funny thing about velocity selectors is it actually doesn't matter what sign you choose your charge to be, because both forces have reverse direction for those two. So we can just pretend it's positive. So if I have a positive charge, it would be attracted to the positive plate. So it's going to have an upwards electric force, which must mean that there's an equal yet opposite magnetic force that's exactly balancing its upward pull. So that does not mean the magnetic field is down, because magnetic field works using the right-hand rule. So remember, we said that if you stick your thumb in the direction of motion and stick your fingers in the direction of the B field, you get your force with your palm. So here we just got to reverse it a bit, or you could just guess. You could just take a 50-50 and see which one works. But my palm has to be going down, yet my thumb has to be going right. So for my palm to be down and my thumb to be going to the right, that must mean my fingers are pointing at me. So that would be a plus Z, right? Because this means at you. So B is actually at you. And then how do we figure out the magnitude? Well, we just do force balancing. So we know that electric and magnetic forces must be equal. Electric force is QE, magnetic force is QVB. Q goes away, so E is VB. So B is E over V, which is going to be equal to 600 divided by the known speed of 2 times 10 to the 4th. And 6 divided by 2 is 3, so we know it's going to be this one. So it's in the plus Z direction, and it is that magnitude, which makes it A. All right, yeah, we're not going to be under time on this, which is fine. It's better that you get a good explanation than me trying to speed run it to do it in real time. So if you wanted me to do it at real speed, I'd just do it all in my head instantly. A charged sphere is centered in the coordinate system shown below. The electric potential is 0, infinitely far away. If the electric potential at point S is Vs, what is the electric potential at point T? Oh, I didn't know. I also said this is level 2. Because you got to do a couple of things. Well, what is electric potential? Electric potential, due to a single point charge, would be KQ over R. So we just need to rank the R for each of these. So S, that's literally one grid box away. So S would be like KQ divided by 1. And what about T? Well, T would be one grid unit this way, and it would be one grid unit this way. So hypotenuse of this, using Pythagorean theorem, would be square root 2. So instead of dividing by 1, we are dividing by square root 2, making that C. So this is a single step, so I would call that a level 1. The electric potential along the y-axis is given by this function. Where is the y component of the E field equal to 0? Well, we know that E field and potential are related, so E points downhill. E points downhill. What does that mean? The y component of the electric field is equal to the downhill slope of the potential function. So I'm just taking the negative derivative of the potential function. And that would be just power rule. Like so. And where is the E field 0? So we're just setting that equal to 0. So 0 equals negative 3y squared minus 6y plus 3. Now, of course, just Desmos this. Just Desmos this, like, get it right. But, of course, this is actually, I picked nice numbers. So we're solving 0. Divide everybody by negative 3, we'd get y squared minus 2y plus 1. So that means that 0 would be equal to y minus 1 quantity squared. So y is plus 1. Now, you actually could have done this a lot easier if you just shove this function into Desmos and see where it has horizontal slope, because that would also correspond to this point. That's what it means physically. Level 2. You don't just take a derivative, you got to set it equal to 0. Consider a wire that does not follow Ohm's law does not follow Ohm's law. As the applied potential difference increases, the resistance increases, which could represent current as a function of potential difference. So normally, if your ohmic resistance, which is related to the slope of this graph, is constant. But this is not ohmic. It says resistance increases. So it actually eliminates C and D, because that would be, C would be an ohmic resistor and D would be just wrong. Who knows? It looked nice for me to draw it for symmetry. We want increasing resistance. So this should be sort of diminishing gains as you keep bringing the potential difference up. So notice that with this curve, sort of over here, you gain this much height as you apply a potential difference near the start. So that's a decent amount of resistance. But if you apply the same potential difference later on, you get barely any gain. So it's actually going to be that one, because it becomes much, much harder to pump current through the circuit as the potential difference increases. And we see that's the opposite effect here, where here, as you apply delta V towards the end, you get a huge jump in current. And if you're getting more and more current, if you're getting a higher rate of increase in current over time, it's going to be a smaller resistance. So how could you have done this sort of qualitatively? Well, if you wanted to model this function, you know that I is equal to 1 over R times delta V. That's just Ohm's law. So it is the reciprocal of the slope of this graph would be resistance. So resistance increasing means this quantity would decrease. So you're just looking for a graph with decreasing slope. Yeah, I'd actually rank this 2, even though it is just like an Ohm's law conceptual question. It's actually level 2 because you have to know what kind of nonlinear it's going to be. Two conducting plates with known area are separated by a given air gap. A potential difference is applied between the plates that we know how much energy is stored between the plates. All right, so this is a capacitor energy storage equation. We can pick our favorite one here. We have potential difference, so we should use one with V in it. And looks like we can calculate the capacitance. So the thing we don't know is charge, so we're not going to do that. So our formulas are as follows. U from a capacitor, the energy stored in its electric field, is 1/2 Q delta V. But Q is CV, so we can write that as 1/2 C delta V squared, or we could write that as 1/2 Q squared over C. Either of these work. We actually want this middle one because we know potential difference, we don't know Q. And we also know what capacitance is. So capacitance is equal to kappa epsilon naught A over D. For two parallel plates. And actually, for our case, kappa is 1 because it's an air gap. So you can see why I say please skip these questions that are calculate based if you have the time for it, because this is going to be quite time consuming. So our stored energy is just going to be the capacitance. So 1/2 times the capacitance, epsilon naught A over D, times the applied potential difference squared. So we just get 1/2 times epsilon naught times plate area divided by plate separation times the potential difference squared. And you can trust that I have plugged that in, and I am getting answer choice B. Again, this is definitely not easy in terms of time, but in terms of steps, it's really finding the right capacitor formula to use and then plugging in for both the capacitance and the energy formula. So I'd rank this nicely at level 2. All right, finally a break here. A small charged sphere is moving in the plus x direction towards these two field orientations. We want to talk about what path the particle will take in each. Okay, so if we look at this, remember our formula for magnetic force is FB is equal to Q V perpendicular B, right? Magnetic fields don't just act on charges, they act on charges moving perpendicular to the B field. So what that means is you actually get no force in orientation 1, because none of that B is perpendicular to V. And if you want to prove it, QV cross B, I can't twist my hand, can't twist my fingers to point in the same way that my thumb is doing that. So no force in orientation 1. And if there's no force, Newton's first law says if there's no forces, no net force, you're just going to go in a straight line forever. And then orientation 2, that's your classic QV cross B. So we're going to get pushed up. So that's going to send the particle. Initially, it's going to get pushed sort of, this one's coming at you. QV cross B. So this actually pushes a force at you. So it's going to start curving sort of out of the page at you, and it makes a circle. So orientation 1 is a straight line. Orientation 2 would be a circular arc. So that's D. And I would classify this as level 2 because you have to understand that you get no force in orientation 1. So magnetic field, magnetic force is about being perpendicular. So I'd rank that it's D. Or sorry, it is D. I'd rank it as level 2. All right. A negatively charged sphere is placed out of a spherical conducing shell. Oh, that's an interesting word. Conducting shell. Which of the following describes the electric field in this cavity with justification? So what do we know? If you have a conductor, please write the 2 things you know about conductors. Inside the conductor region, E is 0. Inside the conductor region, V is constant because E is the slope of V. So if E is 0, the slope is 0, so your V can't change. But we're actually not asked about the conducting shell. We're asked in this cavity region. So what do we know? Well, also remember the fact that the electric field must always be perpendicular to equipotential surfaces. So we actually are going to get some sort of field lines that do something kind of like this. And the only way that you can get this to happen is if you get some sort of surface charges that are going to cluster up in certain spots on the surface to create that perpendicular relationship. Because if E points in the direction of steepest descent, you must be entirely perpendicular to any equipotentials. Now, that actually gives us a justification. So we do actually know it's going to be, this justification is correct. Charges are induced on surfaces because that is entirely how the cancellation happens. It's by surface charges moving around. But is the field 0 or not? Well, this is an example of something called conductive shielding, where if you are surrounded by a conductor, you are ignorant of your surroundings. So this is a Faraday cage, or if they say you're safe from a lightning strike, you're safe from a lightning strike if you're in your car. If you're inside a conductor, you will be safe from any external E fields. So think about it as a literal shield. So point P, the only thing that can affect point P is if you have charges in the cavity with it. It is being protected, shielded from the outside. So it's actually 0 because of charges being induced on the conducting shell. Or the conducing shell, if you will. I would call this level 2. It's borderline level 3 because conductive shielding is difficult. You definitely know it's not this. Electric field does not point away from negative charges. And also you could eliminate D because the potential isn't 0 in any conductor, it's the field. So you could also use a Gauss's law argument and say that, well, there's no enclosed charge in this cavity, so the E field should not be 0. Sorry, the E field should be 0. Because there's no enclosed charges. All right, a thin semicircle with radius r has a uniform linear charge density lambda distributed amongst its surface. We want the electric field at the center of the arc. So remember here that we think about what our different pieces of the arc are doing. So if I look at what this piece of the arc does, that would be a source that way. And if I look at what this piece of the arc does, that would be a source that way. So similar to, this is actually very similar to our triangle problem, where the E fields sort of have canceling components, and we want to extract just part of it. So our expression for a continuous charge distribution would be that E is equal to K times the integral of dq over r squared r hat, where r hat is sort of the component extractor if we need it, and we definitely need one. So here, every segment of the arc is a distance capital R away, and we want cosine theta. No, we do not. We want sine theta. Because we want the vertical, so we want sort of that theta right there. Okay. And then we can do some simplifying. So we know that dq would be equal to lambda times dl, where L is sort of our arc length. And this is one of the trickier parts of this problem is what is dl? Well, this is the distance along an arc called arc length. So if we have a theta here, how do I get arc length in terms of theta? Well, arc length, S, is equal to r theta. we'll call that L to be consistent. So length is r theta. So dl would be r d theta. So we get lambda r d theta as our dq. So now we just integrate. So we'd get k times the integral of lambda r d theta was dq. Then we have r squared down here and sine theta. Our theta ranges from 0 to pi. Because we start with flat parallel to the positive x-axis, then we make it to the negative x-axis. So now we can simplify again, and we would get k lambda over r times the integral from 0 to pi of sine theta d theta, which would be negative k lambda over r times cosine theta going from 0 to pi, which would be negative k lambda over r times cosine pi minus cosine theta, or sorry, cosine 0. Cosine pi is negative 1. Cosine 0 is 1. So we'd get negative k lambda over r times negative 1 minus 1. So this would be negative k lambda over r times negative 2, which would be equal to 2k lambda over r. Wow. That's hard. As if there was any doubt, this is definitely a hard question. Now, some tricky things here would be with units. Forgetting this r, that's a common mistake. And notice the units actually won't work out without an extra r, because this would be q divided by length, this lambda, so you'd get an extra like meters on the denominator. Oh man, back to back. A non-conducting sphere of radius a holds volumetric charge density rho. Determine the electric field a distance r from the center of the sphere, which is inside. So this is saying we have a sphere of charge density, volumetric rho. We want to find the field inside everywhere. Well, this is, of course, Gauss's law. So Gauss's law says that our electric flux, E perp dA, is equal to our enclosed charge divided by epsilon naught. So what is our enclosed charge? That's kind of the harder part. So of course, what surface are we drawing? We're drawing a sphere. So it's just E times A. And then Q enclosed would be rho times V, because we have volumetric charge density, right? That's what rho is. Rho is defined as Q divided by volume. So Q is equal to rho V. So now we can do some substituting. We're taking a Gaussian sphere because we're looking at locations inside the sphere. So we're just going to find a sphere of radius little r. Its area would be 4 pi little r squared, and its volume would be 4/3 pi little r cubed. And we get a whole bunch of cancellations, actually. The 4 pi cancels, and 2 of the r's cancel. So we would be left with E is equal to rho r divided by 3 epsilon naught. Yeah, this is a back-to-back hard question. So actually working this out is pretty difficult. You could get it down to a 50-50 because you know that this is the behavior outside the sphere would be one of these, because electric field is, using the shell theorem, is just going to look like a point charge outside. So you know it had to be one of these two. I will say answer choice B is quite attractive to a lot of people because they think that 3, they don't really see where the 3 would spawn in from. All right. 2 long parallel wires carry currents towards the top of the page. Calculate the net magnetic field at point P, which is located 0.1 meters from each wire. Okay. So we want magnitude and direction. So direction, we can see that my 1 amp current, this magnetic right-hand rule says if you stick your thumb in the direction of current, your fingers wrap with the B field. So actually to the right of the wire, my fingers curl into the page for that wire, and it'll be the opposite for my 3 amp. They actually pop out of the page, and since 3 amps is bigger, I'm going to draw this as a big circle. So I actually know my net field is going to be out of the page. And how do we calculate it? Well, we know that B wire is mu naught I over 2 pi r. So we can do that for each wire. So we can say that B of the left wire is going to be mu naught, which is 4 pi times 10 to the negative 7th, times I, which is 1 amp, divided by 2 pi times R, which is 0.1. And notice the 2 pi's are going to make 2, so I get 2 times 10 to the negative 6th. So this would be 2 microtesla. And now, based on symmetry, we see that the right wire, that just has triple the current at the same distance. So B right is just going to be triple that, which is 6 microtesla. And if we actually wanted direction, this is sort of what we get. So we can see that those subtract, they don't add. So we get 4 out of the page would be our answers there. Because the fields subtract and the out of the page field is bigger. This would be level 2 because it involves superposition. All right, equipotentials. If a positive charge is initially at point O, compare the work required by an external force to move the charge to each of the locations. So we're currently living on this equipotential, this 1 volt line, and we're looking at the work required to push it to each of the other points on here. So we know that the work required from an external force, that's actually just equal to the change in potential energy. Because if you're changing your energy, that must come from somewhere. And if it's not internal forces, which are electric, you must have spent that delta U. That must be the energy you spent to move the charge. And what is U? U is Q delta V. And we are just ranking the magnitude here. I didn't want to make this like a sign question. This was about understanding potentials. So notice actually that A and B are actually both on the 2 volt line. So we know it's actually going to cost the same amount to push you to A and B. So we know that delta V to A is equal to delta V to B, which would be equal to plus 1 volts. And then delta V to C would actually be 0 volts because C is on the same line as O. So it costs nothing to move to C, and it costs something to move to A and B. So that would correspond to answer choice B. I would say this is level 1 because it is just a 1-step thing. You got to read the equipotentials. Circuit shown below has reached steady state. What is the energy stored by the capacitor? All right, so this is trying to this definitely looks like one of our energy formulas, right? This totally looks like U equals 1/2 C delta V squared. So we want steady state, which means this delta V is not the EMF because we're going to be dropping some volts here. So we have to actually do some analysis. So steady state, what does steady state mean? Well, steady state for a capacitor means that C is equal to a gap because after a long time, the capacitor's charged, so it's pushing against. There's no extra charge flowing down its branch to charge it. There's no current down that branch. So we can just quickly redraw this after a long time. (3R) and 6R make 2 in parallel because 1/3 plus 1/6 to the -1 is 2. We'll need that. The capacitor is a hole, so no current goes down there. So this is our effective circuit. So we can see that if we color-coded it, we would get something like this. So we can see why the EMF of the battery is not the same as the capacitor voltage drop, because it is not red to blue, it's yellow to blue, or orange to blue, I guess. So we have to find what that is. Now you can ratio this in your head potentially, but we could say that my total current is going to be the battery EMF divided by Req, which is equal to 3R. So we'd get 1/3 epsilon over R. Cool. And then we need delta V across the capacitor. So delta V across the capacitor, well, that's in parallel with the R resistance. So that would be I R, which would be 1/3 of the epsilon. And now we can finally plug into our formula where U is 1/2 times C times delta V squared, and I'd get 1/2 of 1/9 because I got to square the 3, so I actually get an 18th. Answer choice A. Obviously, this would be 3-star. Yeah, lots of steps here. There are some ways to shorten it. Like if you have the insight that you see that, oh, this R is only 1/3 of the series resistance. So the voltage divider rule would say it's 1/3 of the battery voltage. That works. But of course, I'm showing you the most detailed solution. There's always easier ways to do some of these problems. I'm just showing you the most by-the-book method I can think of. All right, we're halfway done, and I am severely over time. That's okay. Consider a battery with non-negligible internal resistance. So this means it's not really a battery, it's a battery series resistor. A plot of the effective battery voltage versus current applied is shown below. So what terminal voltage is terminal voltage, as I said earlier, it's really the effective battery voltage. So what does that mean? Well, it means by itself, the battery should have an EMF. But due to the fact that there's some internal dropping happening, like this is our model for the real battery, due to the fact that there's some internal voltage drop happening, what this means is that you're going to lose some of your effective voltage due to the Ohm's law IR drop inside. So normal batteries, you don't lose any of your EMF because there's not a resistor in there. But real batteries, there are. So notice that if we graph y equals mx plus b, our slope would be the resistance, as long as we flip the sign, and our y-intercept is going to be the EMF. So it's pretty easy to take a slope of this. So this distance would be 0.5, and this distance would be 2. So our resistance inside would be 2 divided by 0.5, which is 4 ohms. And also note that the EMF of the battery is just going to be our y-intercept. So what it wants is this battery is then connected to a 5 ohm resistor, and it is a real battery with resistance 4 ohms. What's the current? So we'll draw ourselves a real battery. So our real battery is effectively a 5-volt battery in series with a 4 ohm resistor. And then it says we connected this battery to a 5 ohm resistor. So our current, I, would be the EMF divided by Req. And this is just a series of 5 and 4 ohms. So we get 5 divided by 9, which is 0.55555, whatever. So 0.56 amps. This is kind of unique. This is a unique problem. You could argue this is level 3. I put it at level 2. Elimination gets rid of some of these answers. Because I believe if you just, well, you know it's got to be less than this. You know it has to be less than 1 amp. Because 1 amp would be the current if there was no resistance in the battery, so you could be clever. Again, I am showing you the by-the-book way of doing all of these. So you take the slope, and then that tells you a lot about the battery. All right, this segment of wire shown below has length 2L. It's a finite wire. We want the magnetic field at this point. So this is Biot-Savart. So if you see Biot-Savart, you can pretty much do this. Very few easy Biot-Savart questions. So what is Biot-Savart? Biot-Savart says the magnetic field is mu naught I over 4 pi times the integral of dl sine theta divided by r squared, where theta is the angle between the current segment and your point of interest. So all we have to do is we can draw ourselves a point of interest here. And it's actually very important that we remember that the angle theta, we can't pick theta to be whatever we want it to be. We have to pick theta to be the angle that is made between the current segment and the point and like sort of the distance vector. So this is actually theta. So now we can just sort of fill in that this would be a distance y above the midpoint. It varies. And this would be the Pythagorean length y squared plus b squared. So we can actually just fill into our Biot-Savart law that we would get, I think I got to go over here. We get b is equal to mu naught I over 4 pi times the integral. We know we're going from negative L to L because our y can only range L above the midpoint. Go halfway above, halfway below. And sine squared, sorry, 1 over r squared, that would be our like Pythagorean, would be like our hypotenuse squared. And what is sine theta? Well, sine theta is an opposite side, b, divided by hypotenuse, square root y squared plus b squared. So what is that going to be? Well, notice we get a b on top, and we get quantity to the 1 times quantity to the 1/2. So we actually get answer choice D. Because that makes a 3/2 power. Because this would be y squared plus b squared to the 1/2 times y squared plus b squared to the, sorry, y squared plus b squared to the 2/2 times y squared plus b squared to the 1/2, which makes 3/2. And then, of course, dy. Yikes. Now, this one you can actually do by elimination also, because this is 0. This integral is 0. So you know it's the other trig function, because this would be like the odd integral rule, where you're integrating an odd function over a symmetric interval, which is 0. So actually, these two entirely cancel each other out. And then you'd have to remember that if there's trigonometry involved, you get this 3/2 power a lot of the time. So that's tricky, but pattern recognition could help you here. All right, capacitance. Calculate the charge on the positive plate of the 8 microfarad capacitor. Well, this is just a circuit with capacitors in it. So we'll treat this sort of like we did our standard resistor circuits. So of course we know we can do a color-coded potential diagram. And we have sort of our 3 levels of potential. All right. So when we have series or combination circuits, we like to find the equivalent capacitance, resistance, etc., to find the quantity that the battery pumps out. So in this case, the battery, we want like the total charge. So first step is find CEQ. So the equivalent capacitance would be, well, this is a series combination. And 4 and 8 in parallel, remember it's opposite the resistor rules, so these add. So my equivalent capacitance would be 1 over 6 plus 1 over 4 plus 8, which is 12, to the negative 1. And this would be 4 microfarads. Okay? So given that, we can also use the fact that Q total would be equal to C delta V total, which would be 4 microfarads times our voltage, which is 12. So we'd actually get 48 microcoulombs. So that would be the total charge available if we're in series with the battery. So what that tells us is not the answer. It actually eliminates these two, because what's going to happen is, just like current splits via the junction rule, charge also splits via its own junction rule. So we actually know that our charge would be 48 microcoulombs on the 6, and then it's going to somehow sort of split along these branches. So we also have to use the loop rule that delta V across a capacitor is Q over C. So delta V across the 6 microfarads would be the 48 microcoulombs divided by 6, which would be 8 volts. So that tells us that this delta V is 8 volts. So by the loop rule, this delta V has to be 4 volts to make it 12 when we go all the way around. So this is actually also clear if you use your potential values, that if you know you go from 0 to 12 and you drop 8, this must be 4. So Q, so now we'll just use Q equals CV again. Q equals C delta V. Which would be equal to 8 microfarads times 4 volts, which would be 32 microcoulombs. And that would be answer choice B. So we actually kind of eliminated this after we solved for the total charge, because you could see that the total charge was 48 microcoulombs. And you know the charge is split, and this is a larger capacitance, so you got to build up more charge on that one to create the same 4-volt drop. And so you know it was going to be the larger of the two splittings. This was the charge on the other capacitor. What would I say? I would actually call this, I think I still called this level 2. Yeah, I called this level 2 because you could do some clever reasoning. All right, 2 long wires carry parallel currents. We want to find the tension in the supporting string. So let's look at our top wire. So our top wire, it says these wires have mass M. Our top wire, it's definitely going to get weighed down by gravity. So it has some sort of gravitational force, mg, down. Well, also, we know that like currents attract each other. Right? It's not like positive, negative with charges. Like currents actually attract each other. So there's actually going to be a net magnetic force down. So that must mean that the tension in the string has to support not only the weight of the wire, but also a little bit extra. So that's going to be answer choice C. You could use the wire formula, like that kind of looks like Coulomb's law for this, but the only one that fits would be that. This is the very special case that the wires are sort of levitating in place. Like if you manage to get this wire to levitate, it would be exactly 2 mg, but it's answer choice C. 2 star. If you flip the force direction, you get the wrong one. This is actually the normal force on the bottom wire. All right, more magnetic field orientations. Charged sphere moves at speed v through a uniform B field. Consider the 2 scenarios here. All right, so we have a force F in orientation 1. What's the magnetic force in orientation 2? So this, of course, uses the same principle we looked at before, where F is equal to QV perpendicular B. So we need to find how much of our field is perpendicular to V. So in orientation 1, it's entirely perpendicular, right? The V is entirely perpendicular to that field. That's a right angle. So F is going to be QVB, which is equal to 1 QVB, just to show the multiplier. All right. What about orientation 2? Well, F is once again QV perpendicular B, but we actually just need to extract that. So what part of this is perpendicular to the field? Well, the up and down velocity is getting ignored, so we want just this component. So this would be V cosine 30 degrees, which would be V times root 3 over 2. So this would be Q times root 3 over 2, V times B, which would be equal to root 3 over 2 times QVB. And that corresponds to answer choice C. Let's actually see what I said for this one. I said this was 1 star. You just had to extract the correct component. It was definitely not this, and it was definitely not this, so you just had to pick the right trig component. So you had to use the fact that you wanted the perpendicular part to the field. All right. The magnetic flux through a conducting loop varies according to this function. That's cubic. What is the total energy dissipated? We want that proportionality. All right, well, we know that energy dissipated is what you get when you collect all of the power, because power is energy per time. So if you multiply all the power time contributions, you get the total energy. So we got to somehow get power. Well, we have flux, and this is a Faraday's law problem because we know that the induced EMF is going to be equal to the flux dt. And notice that flux is cubic, so this actually means that E is proportional to t squared, because the derivative of a cubic is quadratic. And we also know that power is proportional to EMF squared. So that means that power is proportional to t to the t squared squared, which would be t to the fourth. And then we also know that total energy is proportional to, it's going to be proportional to the power integrated. So if I integrate a fourth power, I would get my energy is proportional to the fifth power. So that's quite a difficult chain of reasoning here, but that does get us to t to the fifth. Probably not a surprise that I would call this 3 star. 27. A coil is connected to a variable current source. Which of the following currents produces the greatest average EMF? So remember that if you have coils and EMFs, this is about inductors wag their fingers. Oh no, you're not changing the current through me. So our relevant formula is that the EMF produced by an inductor is proportional to di dt. So we're looking at the rate of current change. So it looks like in all of these graphs, the current changes over the same interval. It's something over a 0.5 second interval. So we can just sort of rank the current change in each of these. So my first current goes up by 0.4 amps in that interval. My second current goes up by nothing. My third current goes down by 0.6. And my fourth current goes up by 0.4. So since these all happen over the same time interval, we're just ranking which current changes by the most, and that would be answer choice C. Now, really, if we wanted to rank them, like we'd really have like a divide by 0.5 in each of these, but we get the idea. This could totally be level 1, but I called it level 2 because you have to interpret a graph, and usually that bumps it up. A conducting bar is on rails. This is a just bar on rails problem, except it is a ramp rails problem. And we want the speed of the bar after a long time. Okay, so this is a sort of drag problem, because what we know is going to happen is gravity, or at least part of the gravitational force, is going to attempt to pull the bar down the rails. And if you remember from mechanics, or you can just kind of argue, we know it's not the full mg, because part of that mg gets pushed into the ramp and that does nothing. So we know it's going to be mg sine or mg cosine, and looking at the answer choices, I think it's clear which one it is. But we could argue it has to be mg sine, because if you have a large angle, you get a large gravitational force component pulling you down, and if you have a small angle, you get a low component. All right, so mg sine theta pulls down. But also, as this bar goes down the rails, there's going to be a current that starts to circulate. Is it that way? No, I think it's the other way. Whatever. We get a current that circulates. I just drew the wrong thing again. We get a current this way. And if you have a current in a magnetic field, you're going to feel a Bill force. So we have a fighting magnetic force, Bill. And after a long time, you increase your speed, so you increase your current, and these eventually balance each other. So what we're looking for is F net equals 0. So this means that the force down the ramp, which is, what is the force down the ramp? The force down the ramp would be mg sine theta, has to equal the force up the ramp, Bill. And this is a motional EMF problem, which means that the EMF induced would be VBL. So the current would be Ohm's law, VBL over R. So Bill will turn into B times VBL over R times L. So we'd get mg sine theta equals B squared L squared over R times L, or sorry, times V. So we'd get our V after a long time would be mg sine beta divided by B squared L squared. Tricky. 3-star again. Now here's where exposure helps, because we've done a lot of problems that are similar to this, and you should be able to argue that if you have a larger ramp angle, that larger ramp angle means that more mg would be supplied down the ramp, so it should go on the numerator. And also we should just remember after solving the diff EQ a million times that B squared L squared quantity shows up. Doesn't make it any less difficult though. Oh yeah, MGR. There's an MGR here. Oops. All right, charged, isolated, parallel plate capacitor holds a charge Q and has an energy U between its plates. Capacitor remains isolated and we stick a dielectric in. Okay, so before we're going to have charged capacitor, and after we're also going to have a charged capacitor, except there's now a dielectric in. So remember, what does a dielectric do? So first of all, this is isolated. So the capacitor is isolated. So isolated means there's nowhere for the charge to go. So if there's nowhere for the charge to go, that means that Q must be constant. So isolated, what does that mean? This means constant Q. Now, if we have constant Q, but insert a dielectric, what does that do? Well, think about dielectric. Dielectric means dielectric. So the electric field would be weaker for the same charge. So we have weaker field. And if you have a weaker field for the same charge, it's going to decrease the stored energy. And that is consistent with A. I'd rank this 2. Yeah, I ranked this as 2. Now here's how you do it analytically. Is I would choose, since we have constant Q, I would use this capacitor energy storage formula. So my new U would be Q squared over 2C, except I am doubling the capacitance because that is what a dielectric does. A dielectric increases capacitance by that constant. So that's where you get quantitatively the 1/2. I'd use Q squared over 2C for that. Every time I think we've done the worst problem already, it just keeps coming back. And I keep getting reminded that there's harder things here. A rectangular loop of length 2L and width L is placed at distance L from a long wire carrying current I. What is the absolute value of the magnetic flux through the loop? Okay, so this combines flux with B wire. Because remember, B from a wire is not constant. So if I do this, it's going to wrap into the page over here. So I might get a lot of B field piercing that part, less B field piercing this part, less B field piercing this part, and less. So to get the total flux, we have to break this loop into strips of constant flux. So that would be sort of these sort of rectangles where they would have length dx and width L. So again, we know that flux, we can find it if we have a non-constant field by integrating. And the entire field is perpendicular, so we'll just use the expression for B from a wire, which is mu naught I over 2 pi r, and r in this case would be the distance x from the wire that the strip is at, and dA would be L times dx. So now we just have to go about simplifying this integral. So we get mu naught I, L, and 2 pi are all constants. And then we integrate dx divided by x. And now we have to look at our strip distances. So our closest strip distance would be when x is equal to L. And our longest strip distance would be L plus 2 more L's, which makes 3 L's. So we get mu naught I L over 2 pi times natural log of x, right? You're special. 1 over x is special. That goes from L to 3L. So we'd get flux phi is equal to mu naught IL over 2 pi times ln 3L minus ln of 1L. And using the division rule, we could write this as ln of 3L divided by L, which is equal to ln 3. So we'd get mu naught IL over 2 pi ln 3. Sure, that's what we would have guessed, even if there was no multiple choice options, as expected. Yikes, that's clearly in this category. Hard. We can see some pretty reasonable mistakes here in the distractors. All right, 4 spheres with charge plus Q are placed at the vertices of a square as shown below. How much work is required to assemble this arrangement? So what does that mean? Well, this means that like before, we have no energy in the system because before these charges are very far apart. So there's no potential energy between them. But after, they will have potential energy between them. So we're asking what that cost is. And remember that electric potential energy is signed, where if you have opposite charges, you get a negative potential energy because you're in energy debt. And if you have like charges, you would have to, they would pay you, you would have to pay to bring them together. So here we actually end with positive potential energy. So how much work is required to assemble them? Well, it would just be whatever the height of this bar is, U total. So all that to say is that the work done by an external force is equal to U of the system, which would be the sum of all pairs of KQ squared over R, because our charges are the same thing here. So what would that be? Well, so we actually know goodbye A and B because it's not a negative value because the cost, it's going to cost me energy to bring these together, right? It should be a positive value. These charges don't want to be together. That should cost me money. So notice I have sort of 1, 2, 3, 4. I have 4 vertex pairs. And electric potential energy is just 1 power on the denominator. So I have 4 vertex pairs, and then I also can't forget the diags. And those aren't S apart. Those are slightly more than S because it's a Pythagorean. So it's S root 2. And this number, 2 divided by square root 2, that is also square root 2. So it's 4 plus 1.4, which is approximately 5.41 KQ squared over S. I believe I ranked this 2-star because I thought we could get tripped up on the sign. All right, battery, light bulb, and uncharged capacitor are connected in series to an initially open switch as shown. Which of the following correctly describes how the brightness of the bulb will change over time? Okay. So this is about RC circuits. So what happens when we close the switch? So it might help just to draw this circuit at short times and long times. So at short times, remember, our capacitor would be a wire. So we would get a very bright bulb because we get current. And then after a long time, our capacitor would be a gap. So that would mean you are a hole. So we get no current, so this would be off. So what does it do? Well, it's initially bright, then it dims rapidly. And why is that true? Well, we're looking at what happens to the potential difference across the capacitor. So does the capacitor potential difference increase or decrease? Well, notice here that in the short circuit, there would definitely not be a color change across the circuit, but after a long time, or across the capacitor, after a long time, there definitely would be. So there would be no potential difference across the capacitor in short times because all the potential difference is across the bulb. And conversely, there'd be no potential difference across the bulb after a long time because all the potential difference is across the capacitor. Oh, that's a mouthful. This is really just Kirchhoff's loop rule. It's B. Potential difference across the capacitor increases over time. Solidly 2-star. A sphere holding negative charge is launched to the right with speed v0 towards a region of uniform electric field directed also to the right. What describes delta U and delta K? So first of all, we know these two have to be opposites, because if we're just letting this charge be released from rest, your energy budget says that delta K, any gain in kinetic energy, must be due to a loss in potential or vice versa. So we know that these two must be opposites, so it actually eliminates the double ones. So what is actually changing here? So we also know that delta U is Q delta V. Here's actually one way of thinking about it. Do I want to do it this way? I actually think it's easier to do it a different way. That's fine. We'll go this way first. All right, so remember that E points downhill. Electric field points downhill. So this would be negative. This would be downhill relative to this. So what does that mean? That means that we're going through a negative potential difference. So here we have a negative charge, and our potential difference is also negative, so we get positive. So we get a positive delta U, which means we have a negative delta K. Here's an easier way of doing it. Remember that negatives accelerate against the E field. So negatives accelerate against the E field. So if I send a negative charge into the E field, this is actually going to cause a slowdown. So you know your delta K would be negative, and you could have started with kinetic instead. Either way works. I would guess this is probably a 2. Oh no, I said this was a 1. So this was a level 1. Probably because there were 2 ways of getting at it. And if you looked at your energy budget, you could do that. All right, the circuit shown below contains no current. We flip the switch. We want the ratio of the current after a long time to the current after a short time. So let's do that. So this is inductors, which behave oppositely of capacitors. So if we look at short times, inductors are very displeased, right? Inductors do not like you to change the current to them. So after a short time, the inductor is going to behave like a gap, meaning all the current is sort of forced around it, sort of creating a long circuit. So this means our effective circuit would just be this huge perimeter loop. So we get our our current would be the battery EMF divided by Req, which would be 4R, because you have to go through all 4 resistance numbers. Now, what about after a long time? Well, after a long time, inductors are happy because you're not changing the current anymore. Steady state means no DIDT, means happy inductor, so no EMF. And I'm not even going to label these resistors because it does not matter. Because after a long time, notice if we try to color code our circuit, we see that there is a sort of free path for the potential to explore, so it creates a short circuit. So after a long time, you short 2 of the resistors. So our long time current is just epsilon over R. So now we can just calculate this ratio. So IF over I0, after a long time, it would be 1 epsilon over R. And after a short time, it would be 1/4 epsilon over R. So we get 4 over 1. And you could have gotten this down to a 50-50 because you know that after long times, inductors allow current through them. So you know that if you're shorting circuits after a long time with inductors, it has to be one of these like larger than 1 answers. Level 2. Yes, level 2. A long cylindrical wire carries current with density given by this function. Determine the magnetic field strength outside of the wire. Okay, so we have a wire that has some density function J, and we're actually interested in the magnetic field at some point outside the wire. So if it looks like a Gauss's law problem, but it's really about magnetic fields, well, then you know it's going to be Ampere. So Ampere's law says that the magnetic circulation around a path is equal to mu naught times the enclosed current. And this is a circle, so we know we're going to have a magnetic field B circulating for a distance 2 pi r. So what is I enclosed? Well, I enclosed can be found by integrating JdA, because again, J is current per area. Our current density function was beta times r, and our area element would be 2 pi r dr. Because how do you create a circle? You create a circle by rings. Or you could say that area is pi r squared, so dA would be the derivative of the area function, which would be 2 pi r dr. And what are we doing? Well, we're integrating from, we want all of the current in the wire. So we want to go from 0 to the radius of the wire, little a. So we'd get 2 pi beta times the integral from 0 to a of r squared dr. So we'd get 2 pi beta a cubed over 3 would be our enclosed current. So there we go. And then we just solve for b. So goodbye 2 pi, goodbye 2 pi, and then we divide by r. So we get b would be equal to mu naught beta a cubed divided by 3r. So you actually know it has to be 1 over r dependence because that's a shell theorem idea. And the specifics can be found by integration, obviously 3 star. Alrighty, in the circuit shown below, EMF 2 is higher than EMF 1. Rank the potential at A, B, and C. Okay, so it actually is given to us in this problem that EMF 2 is larger. So I should actually write this, that this is large and this is small. So we could do some reasoning here, but I totally sell out to the color model. So it's actually, we should always start a potential actually by defining the ground. So notice I can actually still color the entire circuit blue on the bottom here because the bottoms of the batteries are connected and there's no resistors. So it's a total blue color on the bottom. So I actually do know that C goes last because C is at 0 potential. But what's going to happen here? So actually remember the battery is like a step. It's like a step up in potential. So we actually get our largest possible step up in potential across our EMF 2. So that actually tells us that we get a large step up here. And then we'd actually get a smaller step up here from the first battery. So we get this kind of strange setup where we have 2 batteries, so the potential looks like this. So what does that mean? Well, this would be high, this would be low, and this would be medium. So our highest potential would be B, our medium potential is A, and our low is C. This is clearly 3. Even though it is just a ranking with no math, I think this is conceptually difficult enough to make it a 3 star. Another way you could do it is say that another way you could actually work this out would be to realize that you actually need to drop your entire potential across this resistor to make a closed loop with itself. So you actually know that that actually has to have the entire battery 2 potential difference across it. So we have some sort of intermediate potential here. So actually what's weird about this is since EMF 2 actually wins, you can actually get some current sort of going this way. So the current direction changes to making this very non-trivial. I think it's honestly easiest if you just make up fake values for epsilon 2 and epsilon 1. And if you wanted to really cheat, and you couldn't make epsilon 2 0, that one worked because you could just short. Yeah, it's just hard. Inductance L is connected to a battery, same battery, two different orientations. What is true about the 50% time required, meaning like how long it takes for half of the steady state current to be reached? So anything with time in circuits is, of course, the time constant. So this is inductor circuits. So we want tau is equal to L over R. Tau is L over R. So my first circuit would have time constant L over R, and my second circuit would have time constant L over REQ. R plus R is 2, so L over 2R, which would be 1/2 L over R. So what takes longer? Well, this would be like a half second. This would be 1 second. So T 50% is greater for circuit 1 because it has a larger time constant. I imagine I called that one star. Yes, I did. When an inductance L is connected to a capacitance C, the period of oscillation is T. What capacitance is required to get a period of 3T? So anything with oscillations, we know it's LC circuits, and it's all based on the fact that omega is equal to 1 over the square root of LC. So that's the angular frequency. But remember that frequency and period are opposites of each other in terms of relationship. So it's not totally reciprocal because there's some 2 pi's involved, but we actually know that T is going to be proportional to 1 over omega. So that tells you that T depends on square root LC. So what we know is that we want the period to triple. And we also know that the inductance is the same. So what do we have to do to see? Well, we're asking, what do I have to square root to get 3? So that would be 3 squared, which is 9. So this is a level 2 because you got to know that it's a reciprocal relationship with the formula sheet expression, but the actual plugging in isn't terrible. A negative charge is placed at the center of a cavity surrounded by a spherical conducting shell. The cross-section of a Gaussian surface is shown by the dotted line. Which of the following describes the net flux through the Gaussian surface with justification? So we have 0, non-zero. All right, so remember, this is a conductor, so we can always do our little marking. E is 0 in a conductor, V is constant. Well, I'm asking what the flux is through the surface. So flux is going to be E perpendicular times A, which would be equal to 0 everywhere times A, which is 0. So it's actually A, 0 because E is 0 everywhere. But this should seem kind of odd at first, right? I thought it was phi is Q over epsilon naught. And I totally see a Q in there. But remember that there's the surface charge theorem that says that you will always get a induced charge on the surface of the cavity that sort of stares at the cavity charge to cancel it. So you actually know it's going to be a plus Q that cancels it. So actually, if you computed the net flux, you would get a negative Q in the cavity, but you'd also have a plus Q that lives on the surface. So you actually do get 0 net flux either way. You have to just use that surface charge theorem that in order to ensure that E field is 0, there must be 0 net charge. So it lives on the surface. What is that? I said that was 2. All right, and then we have a quick moment of reprieve. 2 charged spheres are shown below. One sphere has charge 2Q. One sphere has charge 1Q. Determine the location where there would be 0 electric field between the charges if possible. So remember that we'll always use superposition. So this would be a large source of field lines, and U would be a small source of field lines. So we know that if I put the point of interest right at the middle, we know the field wouldn't be zero at the middle because the 2Q wins. So we actually need to place the point somewhere over here to the right of the midline, because if this 2Q is producing a stronger field, we need to get larger distance from it to compensate, to reduce that field. So that's actually going to live in the right half. And I did rank this as level 1. All right, that was more difficult than I remember. That will be reflected in the cut score. So when I give this with my class and I look at how my consistent performers do, I'll make sure to update in the description sort of roughly what each AP score I think would be capable of getting out of 40 in the time constraints. Yeah, so just take note of that. Like, this is graded on a scale. But yeah, I thought this was pretty comprehensive. I think the FRQ should be a lot easier overall than this, because the time is less of a problem there. But overall, I thought this was some pretty good coverage, and hopefully this helped your review.